So in this course, we have studied the rectifier filter circuit. We have simulated it. We know how to design that. We have looked at the waveforms, and then we followed it up with a discussion on non-isolated converters like the buck converter, the boost converter, the buck boost converter. We have looked at the waveforms, the input-output relationship, and also how to design and simulate them. And this was followed by a discussion on isolated converters like the forward converter, the flyback converter, the derived converters, the ones that were derived from the buck, the forward, the push-pull, the half bridge, full bridge, and the buck boost derived converter, which is the flyback converter. And then we discussed on the multi-output converters topic and saw how we address that issue by try to regulate all the outputs of the multi-output controller or multi-output converter. We have also looked at trying to do a PI controller for a single output of the DC-DC converter, and we have also tried to look at the simulation results for a buck converter which is in closed loop. And we have actually seen two topologies, one with feed forward and one without feed forward, and saw the theory behind these control topologies. So I guess now that you would be reasonably sensitized to the DC-DC converter topic. Simulation is an excellent tool. It's an excellent tool for learning. I specifically thought of introducing open source tools in this particular course because it is something that we need to propagate, and many of our students may not be having the means to pay for expensive software. So therefore they should have some alternative, and therefore we chose this topic of doing everything by open source tools. Of course, in Windows you have a lot of tools which you can purchase and which you can definitely use, like MATLAB, PSpice, CatStar, and other equivalent softwares for doing all the simulation and the design work that we went through and discussed in this course. But the emphasis as far as this course was concerned was to do it on open source tools. Simulation and using these open source tools or otherwise is very good. It in fact gives you a lot of insight into the circuit, and it's a good learning platform. However, you must be careful. You must understand that nothing can replace actual hardware implementation on the table. That will give you the maximum insight into the circuit. So gradually I will recommend and suggest that you should go more and more towards implementing on a lab table. There are a lot of issues that even a simulation will not be able to take into account, and the results that you will get are kind of clinical and doctored. So therefore I will say, for example, the EMI issues. In the hardware, in the actual hardware, there are a lot of small things like layout and routing. There will be a small circuit which is in a loop, and then there will be a current flowing through that loop, and because of the current flowing through that loop, there will be an electromagnetic radiation because the loop will act like an antenna, and then this can couple into a neighboring circuit. And this issue is very difficult to show on a simulation or get reflected on a simulation because the models may not be there, and it is highly dependent on other parameters like layout and routing issues. Therefore, you should have consider all these things and have these things in mind when you are doing simulation, and try to use the simulation with a pinch of salt, in the sense that the results that you get from the simulation will consolidate your concepts. It will say your design is right. It can handle so much current. This particular device can handle so much voltage, can withstand so much voltage. And this is the path for freewheeling. This is the path in which the current will take for a particular circuit in a particular time, instant of time. All these concepts can be consolidated and understood, and great insights can be got in this fashion. But the actual working during implementing in the hardware, you will get a lot of other issues and disturbances and uncertainties which you would not have imagined of, like as I mentioned, the EMI and the EMC issues. There could be wiring issues, there could be component layout issues, there could be choice of the component itself, there could be handling of the gate drives, there could be protection issues, voltage protection issues, current protection issues, integration of all these things. So many such small things will add up, and then they can become a major significant problem. And more and more, as you start doing on the lab table, you will start getting more and more experience, and it is like an artist. Though we say all this design is very systematic and has engineering precision in it, when you implement, there is some element of art which comes into it. So it is not only engineering and science, it is also art when you are implementing the circuits, making PCB layouts, and trying to get the results out of that. I hope that you have learned something from this course, and I hope that you are sensitized to DC-DC converters, both non-isolated and isolated, and you know how to go about simulating a circuit using open source tools. And that would be the takeaway from this particular course, the method of getting insight into a circuit, input-output relationship, and the way you would go about simulating the circuit. Using this as the base, you should probably look at more literature and try to understand more deeply into the other topologies and much more different topologies which are available in the literature and papers, and try to study the open a particular broken or damaged piece of SMPS, open them out and try to study what goes inside and things like that one. So that way you can try to investigate and get more insights into the DC-DC converters. Another a very important aspect that I have very briefly touched and sensitized you, but not gone into very great depth, is the part of magnetics. Magnetics is very crucial, both the inductor magnetics and the transformer magnetics, and both the electrical and the magnetic design is actually a very pivotal to the proper working of DC-DC converters. And you have to master this art of designing the transformers and inductors. And more you wind transformers, more and more you take different types of cores, put them together, and then physically wind it with your hand, and then insert air gaps, and then check the inductance values. Keep doing that, then you will get more confidence in building the magnetics. Because in most of the power electronics, in most of the DC-DC converters, the central figure, the central component is not not only the power semiconductor device, but more, in fact, the magnetic components, that is the transformers and the inductor. So you have to pay a lot of attention to that and try to see if you can scale up your skills in trying to make the transformers and these inductors. So with that, I will close this topic, this course, and probably meet you in future again in some other course. Thank you.